Welcome to the deep dive. Thanks for joining us. You've sent over some really interesting material today, articles, notes, all about EMALS.
Right, electromagnetic aircraft launch system. Basically, the new way carriers are launching planes replacing the old steam catapults.
Exactly. And our job today is to really dig into these sources you sent. We want to unpack the technology itself, look at the really tough engineering problems, and some unique aspects of how it developed, strictly based on this info.
Yeah, and it's more than just magnets launching jets, right? It's a window into some serious electrical engineering, massive power management challenges, and how global supply chains play into cutting-edge defense tech. Really relevant stuff if you're into complex systems.
Okay, let's get into it then. What exactly is EMALS? Your sources say it's the advanced replacement for steam. The core idea uses electromagnetic force.
Think of it like a huge, very powerful linear induction motor. Kind of like maglev trains, but flat on a carrier deck and built for incredible acceleration.
And how does that actually launch a plane?
Well, you've got these powerful stator coils laid out along the launch track on deck. When you energize them, they create this rapidly moving magnetic field.
Okay.
And there's a slider attached to the aircraft's nose gear. This moving magnetic field basically grabs the slider and pushes it, and the plane, forward at immense speed.
That sounds like it needs a staggering amount of power, like instantly.
It really does.
Yeah.
The sources mention EMALS has to dump something like 120 megajoules of energy.
Wow.
Yeah, in just 2 or 3 seconds. That's what it takes to get a heavy jet from 0 to, say, 240, 300 kilometers per hour over maybe 90, 100 meters of track.
And the main bits mentioned are the track itself. That slider, a massive power system, serious cooling, must get hot, and a super precise control system.
That's the hardware picture your sources paint.
Yeah, big challenges there.
So if it's that complex, why do it? What makes EMALS better than the old steam method, according to these sources? Well, the materials point to several clear advantages. First up, efficiency. Less energy wasted compared to boiling water for steam, and you ditch all the complex steam pipes and maintenance.
That alone sounds like a big win on a ship.
Huge. Second, adaptability. This is key. Steam catapults are kind of one size fits most, but EMALS can precisely dial in the thrust.
Ah, so you can adjust it for different planes.
Exactly. From lighter drones, maybe 10 tons, up to heavy 40-ton fighters. You give each one the optimal push. Steam just couldn't do that range as effectively.
Makes sense. So it's more versatile for future aircraft, too.
Precisely. The sources also hit on improved reliability, fewer moving parts than steam systems, theoretically fewer breakdowns, smoother launches. That means less stress on the airframes.
Okay.
Plus, you save some space and weight on the carrier itself, which is always valuable.
Right. Now, for the really fascinating part, the engineering nightmare they apparently went through to make this work, your sources really detail the difficulties. What were the biggest hurdles?
Oh, definitely the power management. I mean, storing 120 megajoules and releasing it that fast, that needed totally new energy storage, like huge flywheels or capacitor banks, plus power converters that could handle that massive sudden draw.
And you have to do this on a ship with finite power.
Exactly. You're sharing power with radar, weapons, everything else.
Yeah.
So managing that distribution and timing in milliseconds is incredibly complex.
Yeah.
The sources mentioned early problems on the U.S. Ford carriers needing big software fixes.
And the heat must be intense.
Immense. Needs a very robust cooling system packed into a tight space. Another major challenge.
Then there's the control system you mentioned. Sounds like another headache.
A massive one. The system has to sense the plane's weight, the wind over the deck, other factors, and then adjust the motor's thrust on the fly. Millisecond adjustments.
Wow.
The software needed is incredibly sophisticated. It's integrating tons of sensor data, acceleration, position, temperature, and keeping everything stable in a rough environment. Think salt spray, vibration.
And fixing problems isn't straightforward.
Not like fixing a leaky pipe. Electromagnetic faults are tricky. Need complex diagnostic software. Your sources mentioned the U.S. spent something like, $1.3 billion on the Ford's EMALS? And years debugging the software caused delays.
Okay. And the linear motor itself, designing that magnetic track.
Yeah, just getting a motor to produce that much consistent, controllable force over 90 meters. That's a huge materials and engineering challenge. High precision needed for the coils. And this brings us to the magnets.
Right. The sources emphasize the magnets aren't just a technical component, but their origin is a whole other issue.
Absolutely critical. This is where geopolitics and supply chains really intersect with the tech. You need these super strong permanent magnets, NdFeB, neodymium iron boron.
And often with special additives.
Yes, especially heavy rare earth like dysprosium and terbium to make sure the magnets keep working well at high temperatures.
So what did the sources say about where these come from?
They're pretty clear. China dominates the rare earth scene. The figures mentioned are around 69% of mining, 90% of the processing, and crucially, about 90% of producing the finished NdFeB magnets.
90%. That's a lot of control.
It gives them a huge strategic edge. Lower costs, guaranteed supply for their own projects, like, well, their own EMALS.
And for other countries, what's the implication?
It means dependency and risk. The sources specifically mention potential supply disruptions or export controls, referencing China's upcoming heavy rare export policy in April 2025 as something to watch.
So it affects development elsewhere.
Potentially increases costs and risks for anyone else trying to build or maintain these systems. It's worth noting the sources do mention China isn't totally self-sufficient. They import some heavy rare earths, notably from Myanmar, but the overall picture is one of significant control.
Okay, shifting focus. Your sources also talk about China's EMALS on their new carrier, the Fujin. What are the key facts presented there?
Maybe the most striking thing is that they got EMALS working on a conventionally powered carrier. The U.S. Ford class is nuclear, huge power output, maybe 600 megawatts estimated. The Fujin is conventional, maybe 150 megawatts estimated total power. Big difference.
So how did they bridge that gap for such a power-hungry system?
The sources suggest some real innovation must have happened in their power management, probably highly optimized energy storage, maybe more efficient converters to handle those massive short bursts without overwhelming the ship's grid.
And was it copied from the U.S. system?
The sources characterize it as indigenous R&D, developed from scratch, starting back in the 2000s in Chinese universities and institutes. They had to make their own breakthroughs, especially with some U.S. tech restrictions in place. Fujin's launch in 2022 showed it works.
And they obviously had easier access to the rare earth magnets?
Yes, that's highlighted as a direct benefit. Stable supply, lower cost, maybe even custom magnet designs for better performance. That April 2025 policy your sources mentioned, it kind of underscores their self-sufficiency here.
What about the physical design and what it can launch?
Seems it might be a bit more compact or optimized to fit the Fujin's deck, which is slightly shorter than the Ford's. Track length is thought to be similar, around 90 meters. It's reportedly able to launch their current jets like the J-15, the newer J-35, and future drones, with adjustable thrust between maybe 10 and 30 tons.
Any clues about the control system?
The sources speculate they might leverage their experience from high-speed rail, which also uses sophisticated linear motors.
And the timeline seemed faster.
Relatively, yes. Sources mention about 7 years from the Fujin's construction start in 2015 to the launch in 2022 with EMALS integrated. Compared to the longer, maybe 15-year path for the Ford from concept to initial deployment, it suggests efficient project management, maybe building on existing tech.
One last point from the source's secrecy.
Yeah, that's noted. Unlike the U.S., which eventually releases performance data like the Ford hitting near 99% reliability by 2023, China keeps the Fujin's EMALS specs like exact thrust, cycle time, reliability figures under wraps.
Okay, so to wrap up this deep dive into your sources, what are the main takeaways on EMALS?
Well, based on the material you provided, EMALS is clearly a massive engineering feat. It pushes boundaries in power, control, materials integration, just incredibly complex.
Right.
And the sources show two distinct paths. The U.S., pioneering it on the nuclear Ford, facing early public challenges but achieving high reliability later, and China, developing it indigenously for the conventional Fujin, using their rare earth advantage and showing pretty rapid progress. Both faced huge hurdles, but both got there.
It really is amazing tech. Thanks for bringing these sources in.
Absolutely. And here's a final thought for you, based on all this. Consider how critical breakthroughs or even just control over supply chains in seemingly specialized areas like high-power motors or rare earth processing can ripple out, how they can fundamentally impact huge engineering projects like carrier catapults, and even shift the balance in global technology and strategy. It really connects materials, engineering, and geopolitics in a powerful way.